right, so we're going to start off this week by looking at vectors. Okay, it's like chapter 5, section 4. Okay, so a vector is used to describe two things happening at the same time. Anybody know, what do you use a vector for? It can describe two things about an object. A lot of times we use it for an object in motion, bless you, or a force. Yeah.
Direction.
Yep, vector is used to describe the direction of something, and what else?
Magnitude.
Yeah, exactly. It's magnitude and direction. Perfect. So, an example where you could use a vector to describe something is if you're throwing an object. Okay, the object has a direction and it has a speed. Okay, if you had a force, okay, let's say you're pushing on an object. Well, there's a certain direction you're pushing on. For example, this table. It's different if I push down on it versus if I push sideways on it. That's the direction. And then how hard do I push? That's the magnitude of the force. Okay, another example we could take a look at. If you think about like an airplane. Okay, at any given time, there's tons, hundreds, maybe thousands of aircrafts in the sky at the same time. So it's up to the flight controllers at each tower for each airport to make sure that the planes are not going to collide. Right? He has to kind of coordinate all that traffic in his local area. And this is actually a live map right now of the different planes that are overhead. And if we click on, let's see if we can click on a plane. Sometimes we can click on it, it'll show us kind of where it, okay, so it came from an airport down there, it's heading up. And we can sometimes see how fast it's going. This isn't showing its speed. But we can see its direction and its speed. All right? The other thing that complicates this a little bit is it's in 3D. So you could have two planes, maybe at different altitudes crossing. That's okay. But not crossing at the same altitude. That would be a problem. So you could think of this map as all vectors. Okay? A computer keeping track of the speed and direction of every single plane and making sure that the traffic flows the way it needs to. Right? So it's a little bit more complicated, but we're not going to get that fancy. But that's a use for vectors. Okay, the way we represent a vector is with an arrow or a ray. And the length that you draw the arrow, that represents the magnitude. And the direction that the arrow points, well, that's your direction. Okay, we'll start off by drawing a lot of vectors visually and doing things visually. But eventually we got to come up with a better way to represent vectors other than diagrams, because diagrams are time consuming. They take a long time to draw and they need to be drawn accurately. So we'll start off with a more visual approach, and then we'll figure out other ways to represent vectors. Okay, so suppose we had 2 points. Okay, we'll call the points P and Q. It makes a difference if you start at P and go to Q, or you start at Q and go to P. That's opposite directions, okay? Just like a ray in geometry. And in fact, we use the same notation. So if you wanted to write down a symbol for a vector, you could write that down. It's like the symbol for ray PQ. Starts at P, heads to Q. Okay, the point that a vector starts at, we call that the initial point. And the point that it ends at, that's the terminal point. All vectors, if you're representing a force or a speed, have to have an initial and a terminal point. If it didn't have a terminal point, that means it goes on forever. which in terms of a velocity would mean something going infinitely fast. So it has to have an end, or in the case of a speed, a finite speed. Okay. Sometimes we might even shorten that notation a little bit. Instead of using 2 letters, we'll just represent a vector with a single letter. And if you want to represent it as a single letter, you just put the single letter with a line over it, an arrow. Or you can use a bold letter. Okay, I think your book is going to stick with doing bold letters. For me on the board, sometimes bold letters are kind of hard to do. So I'll try to use the bold letters some of the time, like the book, but I might also use the arrow on top. Okay, any question on that? What a vector is, if I ask you to define that on a test, how you represent it, examples, the initial point, terminal point, or how you represent it.
Can you go back?
Yep. Let's take a look at how we add 2 vectors together. Okay, first thing we got to kind of think about is what happens when you add 2 vectors together. Well, for example, if you take a length in feet plus another length in feet, your final answer is still a length, and it's still in feet. It's just a bigger number. Okay, well, when we add 2 vectors together, we get a new vector. Okay, so adding 2 vectors together gives you a new vector. Okay, one way you could think about that is, let's say that you're pushing on an object. Okay, you're pushing on it at a certain amount of force and in a certain direction. And then let's say you have a friend that's helping you. They're also pushing on that object with a certain amount of force in a certain direction. Well, with the 2 of you working together, you have an even greater amount of force. And if you're pushing in the same direction, the direction stays the same. Now, let's say you were pushing left on something with 50 newtons of force, and your friend was pushing right on something with 50 newtons of force. Okay, what would happen there is you basically would cancel each other out. Your directions are opposite, but your forces are the same. So if you pushed, nothing would happen. Right, so that's the basic idea. Add 2 vectors together, you get a new vector. And this is how you add vectors visually. Okay, to do it visually, you basically have to line up some of the initial and terminal points. So if you want to add together v and w, you're going to position those 2 vectors so that the end point of v and the initial point of w are right on top of each other. And I'll show you an example. So line your vectors up so the ending point of v and the initial point of w are right on top of each other. And then you're going to connect. You're going to connect the initial point of v, okay, where you started, to the ending point of w. Okay, so when you actually do it visually, it's very easy. It's just a lot to try to explain in words. All right, so down below I've drawn 2 different vectors, okay, v and w. Where's the initial point on v? Is it where the arrowhead is or the end that doesn't have the arrow on it? Yep, the one that doesn't have the arrow. Okay, that's the initial point. The terminal point is where the arrow is. Same thing on w. Initial point is the end without the arrow. Terminal point is the one with the arrow. Okay, so let's do what the directions say. We're going to take, and we're going to line up the end point of V, terminal point of V, with the initial point of W. So move those two vectors, so those 2 points, right on top of each other. Just like that. Okay, now you're basically just going to draw in the diagonal, and that's your answer. Okay, so the answer when you add V to W is found by connecting the starting point of V, the initial point, to the ending point of W, and that's it. Just connect those 2 points in the order that I wrote. Initial point of V to terminal point of V. And visually, that's the answer. That's vector V plus W.
It wouldn't have the angle in it.
What's that?
It wouldn't have like a little angle in it.
Nope, the vector, it's always straight. It's always straight. So another way you could think about it is, let's say that you were pushing down and to the right on something. And then you had a friend that was also pushing on that, but he was just pushing right. Well, overall, this is the direction together, this, that the two of you are pushing in. It's down, but it's even further to the right than you were pushing. Any question on that? That's it.
What if W is facing this direction?
If W is facing, sure. Assuming if it was like flipped that way. Yep. So I do the same steps. Just going to move everything over. Take the end point of V, line it up with the beginning point of W. Just like that. Now the last step would be to connect the starting point to the ending point.
Straight down.
Yeah, it'd be pretty straight. Be, yeah, just about straight, just a little bit off. But that would be V plus W. In this case, you're kind of fighting each other a little bit.
Yeah.
All right? You're trying to push down and to the right. Somebody else is trying to push left, so you're kind of canceling out the fact that you're pushing right, and basically it's just going to be pushing almost straight down. That would be the result of the two forces together. Yep. I'm just going to put it back the way we had it. Okay, any other questions on that? All right, let's try this one. Okay, before we even do it, anybody have a thought what's going to happen here? Yeah, it's basically going to cancel out. Think of these as two forces equal in magnitude, same strength, but they're fighting each other. Okay, so line up the ending point of V with the starting point of W. Okay, so let's do that. And now we're going to connect what would have been that diagonal, but look at it. It ends up being the same point. So when you add V plus W here, what do we get?
Point.
Well, what do you always get when you add two vectors together? The type of answer is always a new vector. So you get 0, but we don't get what's called 0 as a number. We get the 0 vector. Just remember, anytime you add two vectors, the answer is the 0 vector. Well, anytime you add two vectors, the answer is a vector. In this case, 0. But you're right, visually there's really, there's no way to draw that. That's the only way to represent it. Okay, we might talk more about that later on. Any question on that? Just make sure you don't write this as the answer. That's a number. That's not a vector. So when you started, probably in Algebra 1, you learned those basic properties, 5 plus 2 and 2 plus 5, same thing. Well, we can do the same thing with vectors. Okay, vector addition is commutative, and it's also associative. So commutative means you change the order you add them in. Okay, so let's do v plus w. Let's get that answer. And then we'll switch it around and do w plus v. Okay, so to do v plus w, line those 2 points up. Okay, and our final answer, connect the beginning to the end. I'll move it off. That's v plus w. Again, the v and the w there, they're bold. They represent vectors. Now let's switch it. Let's take w and add v onto the end of that. Right, so I just switched the order that I added them up in. If you look, they're the exact same thing. Right? So whether you do v plus w or w plus v, it comes out exactly the same. Any question on that? This is pretty straightforward. Right? It shows it's commutative. Okay, let's look at associative. Okay, to do associative, I need three things. An associative doesn't change the order, it changes the grouping. So what we'll do on the left is we'll take vectors A and B and add them up, get an answer, then add C to it. And then on the right, we'll add B and C first, get an answer, and then take A plus that answer. Okay, so there's my three vectors, okay, A, B, and C. Let's do it on the left first. So take A and add B onto the end of it. So there's A plus B. And now what does it say we're going to add on to A plus B? C. Okay, just add C right onto that. Take C, add that on the best we can, and connect where you started to where you stopped. And that's your answer. So that vector right there represents A plus B plus C. Any question on how we got that? So let's try the same thing, except do it in a different order. Let's do B plus C first. So there's B plus C. Oops. Line those up the right way. B plus C. Make sure when you do it, you always go from the start point to the end point, not the other way. Okay, and what does it say we're going to add on to B plus C? Yep, this time we're going to add A. Okay, so take A, that's A, and on the end of it, I'm going to put B plus C. And now connect beginning to end, and let's see if we get the same number. And it's not perfect because we just estimated it. That's pretty close. It's pretty close. And so the whole point of that is just to show that when you add vectors, it's both commutative and associative. Eventually, we're going to get away from doing this visually for one of the reasons I just showed you. If you don't sketch it perfectly, things don't line up perfectly. Okay, and it's very time consuming if I'm going to get out a ruler and try to measure or use a grid. Okay, it's going to take too long. All right, so we need a better way besides this visual stuff. Okay, and we'll get there eventually. Okay, so we talked a little bit about this earlier. This is written more as an equation rather than a picture. But if you take a vector and the opposite of that vector, you get the zero vector. What would be the difference between V and negative V? Direction. That's it. Direction is opposite. How about magnitude? Same. Yep, magnitude is the same. So direction is opposite. Magnitude is the same. And it doesn't just have to mean that one point's up and one point's down. It could be just whatever opposite is. Okay? Whatever opposite is. And this idea that we just had here is how we're going to have to do subtraction. Okay? V plus negative V. It's exactly the same thing as saying V minus V. So when we want to do subtraction, the way we're going to do it is we're going to make it into addition, but you're going to add the opposite. Okay? When you started out learning about how to add and subtract negatives, you might have learned that method. Instead of doing 5 minus 2, you can think of it as 5 plus negative 2. Same idea. Okay, so to subtract two vectors, find the opposite of the second vector. That makes it negative. And then add. Here's an example with numbers again. That's the idea we're going for right here. Find the opposite of the second one, and then change it to addition. So they want me to do V minus W. What's the first thing I have to do if I want to do V minus W? Yep, find the opposite of which one? Yeah, in this case that is W. And what does opposite mean? What's that going to do to the vector?
Change the direction.
Just going to change the direction. It's like it's going to point 180 degrees the other way. Okay, so let's find that first. So what I'll do, make a copy of it. This part I can do exact. What I have to do is flip it horizontally and then flip it vertically. And that keeps it exactly the same length, but now it points the other way. All right, so now I've got negative W. And what do I do with that? Yeah, I add it. Add it to what? Exactly. You're going to think of it like this now. Okay. You've got V, you've got negative W. Just add them together. And that's like doing subtraction. So here's V, negative W, and draw your answer. If you can. Okay, that's as good as I can get mine. That's it. That's V minus W. Okay, any question on that? All right, so we looked at addition, we looked at subtraction. Now we're going to look at a product. What we're not going to do yet, we're going to save this for probably Wednesday. We're not going to multiply two vectors together. That's a little different. What we are going to do, though, is look at scaling a vector. Okay, what does it mean to scale something? What does that mean, to scale? Scale something. Yeah, Owen? Okay, so yeah, sure, that's one way, if you scale a mountain, sure. How about in terms of like a model? Like if you had a scale model, what does that mean?
To size.
Yeah, it's a smaller version of it. Okay, it's exactly the same as the original, except it's a smaller, or it could be larger. It could make a larger scale or smaller scale. So a scalar product is when we take a vector, we basically multiply by a number. Okay, that number is called the scalar. And the answer that you get here is still a vector. It's just either a larger one or a shorter one. Now, if you multiplied by 0, that would take your vector and basically get rid of it. You'd have the 0 vector. Okay, so when you scale a vector, your answer is still a vector. It's just longer or shorter than what you started with. So I said it can shorten the vector, it can lengthen the vector. It could also reverse the direction. How could a scalar reverse the direction? What would you be multiplying by that would do that? Negative what? Yeah, negative 1. But that's all that a scalar can do. Shorten it, lengthen it, or it can reverse the direction if you multiply by a negative 1. All right, so first example they give me is 2 times the vector v. Hey, Ashley, do you think that's going to make v longer or shorter?
Longer?
Yeah, how much longer?
How?
So 2v would make, oh, how would 2v compare to v? It would be twice the size, yeah. The original would be, I guess, half the size, if you think of it that way. Okay, so finding 2v, that's very easy. Just take v, take another v, add them together, and draw in your final answer. There's 2v. If I didn't have a smartboard, what I'd have to do for some of this is use like graph paper. And I just measure the length on the graph paper and double it. That's all. Okay, how about half v? Zach?
It would be half the size of v,
How about the direction compared to v?
same way.
Same direction, yep. Okay, half v, I don't really have any way I can shrink a vector easily, so I'm just going to have to estimate best I can. So there's a half v. Okay, same direction, half as long. Okay, any questions on that? So what's that number called in front of the vector again? That's a scalar. Okay, think it scales the vector, larger or smaller. Scales it. And together, this whole thing is called a scalar product. Okay, I think we kind of jumped ahead a little bit. We already talked about what happens with the negative. Anybody tell me how negative 1v is going to compare to v? It's going to reverse direction. How about the length? Same length. In fact, we already had to do this when we did subtraction. All right. So take your vector, flip it, and flip it. Again, if I was doing this on graph paper, it would be very easy. I'd just trace over it and draw it the other way. Okay, how about negative 1/3 v? Emily, how's that going to compare to v?
It's going to be one third of it, it's going to be going in the opposite direction.
Yeah, the length is going to be 1/3, and it's going to point the opposite way. Again, I don't have an easy way to do that, so just take negative v, which already points the opposite way, and try to draw it 1/3 as long. So maybe something like that. Okay, any question on that one? All right. So now let's take the idea we did earlier with addition and combine it with a scalar product. So I want to find 2v plus 3w. Okay, and the way you want to think about it is break it down into steps. What do you think the first thing I want to find here is? Before I can even really do the addition. I've got v and I've got w. I should find 2v. Okay, find that first. Hey, anybody explain to me, how do I get 2v using the smartboard? What can I do? What's the idea? How about Naisha? How do I get 2v? I've got v. Would I flip it? Would that give me 2v? Anyone help her out? How about Paige?
Double it.
Yeah, I double it. So how would I double it? What would I do?
Make a copy.
Yeah, just take v, make a copy of it, and put two of them together. There's v. There's 2v. In fact, what we can do is, we don't even have to trace and make a vector, just leave it like that. So there's 2v. And how about, Brandon, what am I adding on to 2v?
3w.
3 of the w. So do exactly what it says. Take 3 of the w. So there's 1, 2, and 3. Does it matter that I didn't go back and copy the original one each time? I made a copy of the copy. Did that make a difference? No. They're all copies of each other, so that doesn't matter. And then make your final answer. Usually what I like to do after is just pull it away so you can see it. Right, so there's combining a scalar product with addition, or you could do the same thing with subtraction. All right, so sometimes we don't really care about the direction that a vector is pointing in. We just care about how long it is. Okay? Its magnitude. That's what that symbol means. So if you see a vector and it's got almost looks like double absolute value bars. They're not absolute value bars, but that's what they kind of look like. That symbol means the magnitude of the vector. How is the magnitude of a vector represented? A length or a number, yeah, exactly. So the answer to this kind of problem is a number. Magnitude is a number. And somebody else said it's length. Well, if it's length, length is always positive. You'd never say that your vector has negative magnitude. That doesn't make sense. And if it has a negative in it, that's the direction. Right? But the magnitude or the length, it's always positive. Let's look at that. The magnitude of x versus the magnitude of negative x. What's the difference between those two things? I think they know that. What's the difference between the magnitude of x and the magnitude of negative x? Well, Josh? Well, let's just start out, pretend the magnitude wasn't there. What would be the difference between x and negative x?
One's positive and one's negative.
So what would that mean visually? Like if you drew the arrows?
One's going down and one's going up.
Okay, so they're pointing opposite directions. Okay. What about their lengths? X and negative x.
They're the same.
They're the same. So this symbol right here, the double bar, just means what's the length of x compared to the length of negative x?
So it's the same.
It's the same, yeah. They are the same. Right, there is no difference. Same thing. If your magnitude comes out to exactly 1, that has a special name. That's called a unit vector. Remember when we studied unit circle? Unit circle was a circle that had a radius of 1. So anytime you have the number 1 involved, we usually use the word unit to represent that. Another place you see that is when people describe like the speed they're driving at, like 50 miles per hour. That's a rate of speed. Specifically, it's a unit rate. You said you're driving 50 miles per 1 hour. You didn't say your speed was 100 miles per 2 hour. That'd be kind of a weird way to say your speed. Okay? So unit represents 1. Any questions on that? So if we're going to start to really do a lot of addition, subtraction, and other algebraic operations on vectors, we need a better way. Drawing all these pictures and diagrams, it's going to take too long. It's too much work to try to draw it perfectly. So we're going to come up with a different notation. Okay, this is called an algebraic vector. Okay, when we write a vector in this notation, okay, what you do is you use an angled bracket on the left, an angled bracket on the right, and you're going to have two numbers, a, comma, b. What a is going to represent is the horizontal distance between the initial point and the terminal point. It's the horizontal. B represents the vertical distance between the initial point and the terminal point. It's almost like kind of finding slope, except you're not writing it as a fraction. So you're finding a horizontal distance between 2 points. And a vertical distance. And what we call those two distances, those are your components. Okay, every vector has a horizontal component and a vertical component. In that case, that's a vector that has both components and neither one of them is 0. If you drew a vector like this, straight down, that has no horizontal component. Okay? All it does is go vertical. Okay? So if a vector goes straight up or straight down, there's no horizontal component to it, just vertical. Likewise, if it just goes left and right. If it just goes left and right, that's a horizontal vector. There'd be no vertical. This is everything that I just drew in the diagram. Okay, so from an initial point, A tells you how far left or right you go to get to the terminal, and B tells you how far up or down you go from initial to terminal. Okay, any questions on that notation? Okay, that's called the algebraic notation for a vector.
So that's how we're going to do it basically?
This is one notation we can use, yeah. There's really 3 ways we can do it. There's drawing it. Okay, we already did that. There's this notation. And then there's one more we'll do tomorrow, which is the one they use most often. But it's very similar to the one we're doing right now. Okay, so let's say I wanted to draw that vector. First of all, why can't I just use parentheses? What would happen if I put parentheses around that? That's a point. That's a coordinate. If you want to write something as a vector, you've got to put those brackets. Now, when we do algebraic notation, did it say anything about where you have to start? Where the initial point has to be? What do you think, Sarah?
Like I would think 0, but
So you'd think maybe the origin would be a good place to put it, but did it say that anywhere in here? No. So if they ask you to draw that vector, I could start there if I wanted. The only requirement is that I go 3 right and 4 up. So there's a drawing of the vector 3, 4. Okay. Here's another one. Has an initial point and a terminal point, 3 right, 4 up. Any of those vectors represent 3, 4. Okay, including, including that one. And if we put it at the origin, that's usually the best place to put it. Because if you have an initial point that's 0, 0, it makes anything easier in terms of arithmetic. So I want you to think of this notation, it's kind of what we call a relative notation. It tells you the horizontal and vertical component, but it doesn't really tell you where to put it. Okay? But if it does start at the origin, that's called a position vector. Okay, so if your initial point is at the origin, that's a position vector. Okay, let's see if we can figure out how to find the position vector if they give you a vector that's not at the origin. What I'm going to do is get rid of some of these other vectors. Let's just look at one of them. Let's say they gave me the coordinates of the initial point and the terminal point. Let me make it, I'll scroll back down, but let me make the graph a little bigger. Okay, what's the coordinate of my initial point?
2, 6.
Yeah, 2, 6. How about my terminal point?
What about you subtract?
5, 9. So the goal is to somehow figure out how could you get that vector using those 2 points? What could you do? Let's start with just the 3. Okay, look at how you could get the 3 based off the 5 and the 2.
It would be that.
Is it 5?
6 plus 4 would be 10.
Actually, you know what? I think the 9 is right. We were off. Whoever said, yeah. So that might have thrown me off a little bit. Now, what could I do with the 5 and the 2 to get a 3? Yeah, subtract them. How about the 9 and the 5? Subtract them. And that's exactly how you find what I was just talking about. Okay, if you want to find a position vector, in other words, you want to find where the terminal point would be. If you took this vector and moved it to the origin, it's 3, 4. All you have to do is subtract the coordinates that you're given. Okay, let your initial point be x1, y1. Let the terminal point be x2, y2. And that's how you find a position vector. You do have to subtract in a certain order. Terminal minus initial. Terminal minus initial. What would happen if you switch the order? What would that do to your vector? Yeah, it would flip it. It would point the wrong way. It would be pointing the opposite of the way that you want. Okay, so if they give you 2 points and they don't label which one is initial and terminal, assume that P1 is initial and P2, the second one, that's your terminal. Let's see if we can find our position vector. Okay, Michaela, can you tell me what the calculation will be to find the x, the horizontal?
4 minus -1.
Good. 4 minus -1. Don't forget, you got a minus from the formula and a minus from the -1, so that's perfect. Okay. Andrew, how about my calculation to find the vertical component?
It would be 6 minus 4.
6 minus, I think you gave me the final answer.
Probably.
So 6 minus 2, yeah, 6 minus 2. Okay, so yeah, when you do that out, 4 minus -1 gives me 5, 4. So if you were to sketch that vector and you wanted to have it at the origin, put the terminal point at 5, 4, and draw your arrow from 0, 0 to 5, 4. Okay, and that's finding a position vector. Any question on that? Okay, so I think that's pretty good. So that's the first part of 5, 4. So for tonight, in your book on 344, okay, I want you to do 1 and 8 to 22 even. On 26 to 32, you just do the evens, but don't follow the directions in the book because you don't know how to do what they're asking there. Just find the position vector. Okay, so for 26 to 32, just use my directions. Just find the position vector.